Alright guys, I need to give you some centers of mass stuff, and it's not actually hard, there's just one thing that's hella confusing. So, what I'm going to be talking about is I have some blob like this in the plane for starters. Right? Later we'll do kind of more complicated three-dimensional objects, but it doesn't get any different. So, the thing you need to know here is that if I envision this guy as tipping on the plane, right, I want to think about where I would put a stick underneath this to balance it out, right? And so what I'm going to get is I'm going to get some point, right, maybe here on this guy, that's the center of mass of this object. And that's going to be at x bar, y bar, right? Not vectors, but a point, x bar, comma, y bar. And that's going to be where you could balance your plate on a stick, right? So if I want to actually calculate that, I need to know three things. The first is just where to get the mass of the plate, like the total mass of the whole thing. And the way to get the total mass is you just integrate over the thing that I'm going to call R. And so R is going to be a region in the plane. And the thing you want to integrate to get the mass is the density function. And what you should think, right, is that you're integrating over maybe the x's first and then, or sorry, the x's first and then the y's. So your dA would be dx dy. But there's no reason that you have to do this in Cartesian coordinates. You could switch this to polar and that would be just fine. If you do switch to polar, right, then you would have sigma of r and theta. And your d area would be r dr d theta, right? Okay, anyway. However you accomplish this integral, that'll give you the total mass of the plate. And then if you want to talk about the tendency to tip over the x, and this is the part that gets confusing, x bar is going to be my over m, which is, well, on the bottom here, I have just a double integral of the region of the density function with respect to area. Right, that's the m I just told you about. And then my is going to be the tendency to tip over the y-axis. And so the tendency to tip over the y-axis is a thing about x's. So that's going to be the double integral over r of x sigma of x and y d area. So whatever your density function is going to go in here, and then it's going to be weighted by x. Right, that's really just saying the further out something is, the tippier it makes it. The confusing bit is that this means that my, that marker's dead. The confusing thing here, right, that marker's also dead. Good prep, Joe. So the confusing thing is that my is about x's. Right? The moment around the y-axis is a thing about x's. And so then we do our y bar, and y bar is just mx divided by m. But of course mx isn't weighted by y, or isn't weighted by x's, it's weighted by y's. So you'd have the double integral over r of y sigma of x and y d area divided by the mass again, which is the double integral over r of the density function with respect to area. And then if you want to scale this up to 3D, which I'll mention very briefly even though there's no homework on it, you do something like the moment about the x and y axis, right, would be the triple integral of z density function of x, y, and z d volume, right? And you would use this to calculate the z moment. So you do z bar is mxy over m. And you'd make m in a very similar way, right? You just triple integrate the density function with respect to volume instead of area. But for right now, the ones I need you to have are these guys. So x bar is my over m, and my is calculated by weighting with x's, not with y's. Cool?